a fun consequence of Green's theorem is that we can use a line integral to find the area of this bounded region R and R2 enclosed by our curve C. So Green's theorem tells us that the integral over the closed curve C of x dy is equal to minus the integral over a closed curve C of y dx. And we combine these two together to give us the line integral 1/2 of the 1/2 multiplied by the integral over a closed curve C of x dy minus y dx. And so we use this consequence to find the area of the region. So where does this come from? So this consequence of Green's theorem arises when we're working with the following vector fields. So we have two separate cases here. We have the vector field f is equal to the vector with components 0x and the vector field f defined by the components y0. So let's take a closer look at where this formula comes from. So here we are exploring how we are able to establish the area of a bounded region R using Green's theorem. And we have two separate cases here. So in case 1, we want to suppose that the vector field f that we're considering is defined by the components 0, 1. And keep in mind here that we are using an alternative form of our circulation vector line integral in order to do this. So we want to set these double integrals and this vector line integral up. So here we go. We have that our f component in this case is 0. Our g component here is x. So the partial derivative of f with respect to y is just 0. The partial derivative of g with respect to x is 1. And so therefore we can see that the curl here is going to be 1 minus 0, which leaves us with 1. We're also going to use these f and g components in the vector line integral. So we can say by Green's theorem, we have the vector line integral over the closed curve C of f dx, so that's going to be 0 dx, plus g dy, so we have x dy, is equal to the double integral over the bounded region R of the curl, which we found to be 1 dA. And looking at this double integral here, we recall that since the integrand is 1, that this double integral is simply equal to the area of that bounded region. So we're able to conclude here that therefore the area of this bounded region by R, or of R, by Green's theorem is equal to the vector line integral over the closed curve C of x dy. So here is the first consequence of Green's theorem for the area. But we also need to go ahead and consider case 2. And so here we suppose that the vector field is defined by the vector with components y0. And we want to apply Green's theorem here just as we did in case 1 again. So we have our f component is y, our g component is 0. So taking the partial derivative of f with respect to y, we end up with 1. The partial derivative of g with respect to x is 0. So therefore, the curl is going to be equal to 0 minus 1, which leaves us with negative 1. And so by Green's theorem, we have the vector line integral over the closed curve C of f dx, so it's going to be y dx, plus g dy, so that's 0 dy, and this is equal to the double integral over the bounded region R of the curl, which we found to be negative 1 dA. And using that same logic that we did up in case 1 here, since the integrand is negative 1, we simply have attained minus the area of this bounded region R. Woohoo! So we can see here that minus the area of R, that bounded region, this is equal to the vector line integral over the closed curve C of y dx by Green's theorem But of course, we don't want a negative area. So we're going to multiply both sides by -1, which gives us, we can say, therefore, the area of R by Green's theorem is equal to minus the vector line integral over the closed curve C of y dx. And so we have attained a second vector line integral by Green's theorem for the area. So what we want to do now is combine these two bad boys into one happy integral. And so here we go. So recall, from case 1, we found that the area of R is defined by the vector line integral over the closed curve C of x dy. And then in case 2, we saw by Green's theorem that the area of this bounded region R is also equal to minus the vector line integral over the closed curve C of y dx. So if we were to just add these two together, right, we would end up with 2 times the area of R. And we'll give ourselves a little bit more room. So if we were to add these up, we would have twice the area of R is equal to the vector line integral over the closed curve C of x dy plus, a positive multiplied by a negative is negative, or minus the vector line integral over that closed curve C of y dx. Right, we can also just rewrite this. Let's pull that vector line integral out. So I have x dy minus y dx. But again, we don't want twice the area. We just want the area of R. So using a little algebra, we divide both sides by 2. And we have that, therefore, the area of R by Green's theorem is equal to 1/2 times the vector line integral over the closed curve C of x dy minus y dx. And so there you have it. Area by Green's theorem. How fun.